Hello everyone, Rugved Nakade here from torsionaltraining.com. I have a pretty awesome lesson for you guys today. It's Module 3, Lesson 3. I'm going to show you how to build a full model. I have a motor driving a pump through a coupling, and the good thing is that I have the full model with the geometry information, so we're not actually going to use the mass elastic method in this case, so I think you'll really get a kick out of this particular lesson. So let me get started. The what I've pasted here is a table of all the geometry information of this motor. So we have a motor driving a pump through a coupling. Now I wasn't able to provide you the actual shaft information and drawings because the manufacturers would not give me permission to display them to you. So, but I have extracted all the geometry information and I've pasted them for you here. So you should be able to do the analysis with this geometry information from the table. So without further ado, I'll fire up diarobes and we'll get started and model this in, and then we will go from there. See you in diarobes. Okay, so I have diarobes fired up here. So let's get started. Since we have three uh, different components, a motor, a coupling, and the pump, the first thing I like to do after selecting my units is to pick different materials. So first let me put in our description. So we've got motor, driving, pump, through, coupling. Okay. And let's pick our material. And material 1, then you pick material 2 here and click select again and it populates your second row here. So, and then click on material 3 and click select and it populates your third row here. So the first material we're going to assign it to the motor, the second material will be assigned to the coupling, and the third material will be assigned to the pump. So after populating your materials, go ahead and click on shaft elements and let's start modeling in this motor, coupling, and pump information. So element number 1, sub 1, material 1, level 0, length will be 4.9, mass ID will be 0, mass OD will be 5.512, stiffness ID will be 0, and stiffness OD will be 5.512, and call this step 1. So we are now modeling the motor. So what I like to do is every element in the motor, I like to call them steps because, most of the motors that are out there are stepped shaft motors. So I just like to call them step 1, step 2, and so on forth. You can obviously call it anything that you want. So element number 2, sub 1, material 1, 0. Length is 3.98. Mass ID is 0. Uh, Mass OD is 4.921. Stiffness ID 0. And stiffness OD is 4.921. Step 2. Right? And so, if you follow all these elements shown here in the Excel spreadsheet, your final shaft element should look like this for the motor. Right, so I have all the 24 elements modeled in for the motor, and your shaft looks pretty cool. So hit save, call it example 1, so I'll call it example 1, and close, and there's your motor. So here's your motor shaft. Now, one thing I'd like to mention, the industry typically likes to model from where the power begins to where the power is transmitted. So, for example, if you have a motor, your motor is your driver. So, generally modeling, it's just a convention that people use, tend to prefer to model from the driver to the driven machine. So that's why I started with the motor. In my previous modules, you've seen me start with especially in the case of the motor, in the last lesson, I started with the drive end of the motor and I modeled to the non-drive end of the motor. But typically, what everybody prefers to do in the industry is to model from the non-drive end of the driver all the way to the non-drive end of the driven machine. So that's the convention that I'm following for this particular model. Anyway, so the first 24 elements and 25 stations belong to the motor, and then we will go in and now model the coupling. So click on Model, click on Data Editor, click on Shaft Elements. Okay, so next we'll model the coupling up, and the one different thing about modeling the coupling is, remember, in our material population, we gave the coupling material number 2. So the only difference when we model the coupling will be to pick this material column as number 2. So let's get started on that. So 25, 1, material 2, level 0. The length is 3.75 inches. The mass ID is 0. The mass OD is 9.25 inches. Stiffness ID is 0. Stiffness OD is 9.25 inches. And make this hub 1A. Then 26, sub-element 1, material 2, level 0, 1.125, mass ID 0, mass OD is 12.5 inches, stiffness ID 0, stiffness OD is 12.5 inches, hub 1B. 27 is length of 1.125 inches. The mass ID is 5.75 inches. The mass OD is 12.5 inches. And now, since we're building a spacer, it's going to also have a stiffness ID of 5.75 inches and a stiffness OD of 12.5 inches, and call this spacer. 28 will be 6 inches length and 5.75 inches mass ID and 6.5 inches mass OD. Again, 5.75 inches mass ID or stiffness ID and 6.5 inches stiffness OD. Call this spacer. And your final model for the coupling should look like this. Right, so there you go. So I've put in the hub information, the spacer information, and the second hub information. Go ahead and click Save, Close, hit Yes, and there is our coupling. Notice, because we gave it a different material number, it has a different color for the coupling. And once we assign the pump, it'll again have a different color. And so we've now got the motor coupled to the coupling, and the last thing we need to add is the pump. So let's go ahead and do that. Click on Model, Data Editor, go back to the shaft elements, and I have the motor to the right of the coupling. And so number 32, sub 1. Now remember, this is the third material, so material 3, 0. The length is 4.113. The mass ID is 0. The mass OD is 3.07. Stiffness ID is 0, 3.07. And call this pump 1. And your final mass elastic table for this particular pump will look like this. So here is the mass elastic information, or sorry, the geometry information modeled in for the pump. And I wanted to show you the last element for the pump. So click number 37, 1, material 3, 0, and the length is 1.65 inches, and the mass ID is 0. And check it out. This OD is 28.9698, and it's a pretty big impeller, so that's why the diameter is large. The stiffness ID is 0, and again the stiffness OD will be 28.9698 impeller. So, the first thing that comes to mind as soon as you see a number that looks odd like that, 28.9698, I mean that's accuracy to the fourth decimal place. I mean, is it really possible to have such an accuracy in the measurement of the diameter? Not really. So I think what's happening here is the pump manufacturer has converted the inertia information of the impeller and has put it in equivalent length and equivalent diameter properties to make it represent the inertia and the stiffness in the actual system. So really, this is a not a very I mean, this is a very accurate number for a diameter. So it makes you wonder if it truly is what they say it is. But I think what they did here is they went in and they did some calculations, and then they came up with an equivalent diameter and an equivalent length to give you the effective inertia and effective stiffness in the particular impeller. So click save, hit close, hey yes, and there is your pump, which is in blue color, and this is the shaft of the pump, and this is that big impeller, that big diameter that we've added here. And there's your full model. So we've put together a full model. We have a motor driving a coupling, driving a pump through a coupling. Now, there are a few things that we need to add in this model. If you recall from our previous lessons, we still haven't added the inertia of the core of this motor. And if you recall, when we modeled the coupling in the previous example, we had to make some adjustments for stiffness and for inertias to get the right coupling inertia and coupling stiffness modeled in. So let's go ahead and put these two pieces of information in, and then we will have the final model built for this particular machine. So in this Excel spreadsheet, I have a tab for major inertias and stiffnesses, and I have the information for the total motor core inertia, which was 862.53 pound-inch second squared, and it lies in this region here between stations 13 through 16. So that's why I put it here as stations 13 through 16, and the unit is also pound-inch second squared. And if you recall in the last module where I show you how to model the motor, you split the inertia value of the motor core into 3 or 4 stations. So you basically distribute it over the length of the core. That's one method of doing it, and there are some more advanced methods of modeling this in DIROBES, but for our purpose this will do just fine. So what I do is since there's 4 stations between 13 and 16, so 1, 2, 13, 14, 15, and 16. So I took the value of 862.53 and I divided it by 4, and so I have 215.63 pound-inch second squared to be added at every station. So let me go to model, go to data editor, and I think we all know how to add disks by this point. So click on disks, type rigid, station 13. The polar inertia is going to be 215.6325, so 215.6325, right? And call this core by 4, right? Since we're dividing the core inertia by 4. Rigid 14, same thing, 215.632, and again core by 4. Rigid 15, core by 4, rigid 16, 215.632, and core by 4. Right, so now we have the inertia of the rotor core modeled in. So click on save, hit close, hit yes, and there we go. These are the inertias that have been added for the core. Now, the last thing we would like to do is we would like to add the stiffness information of the coupling in this model. Modeling the stiffnesses of the coupling is a little tricky for this particular model, and this is because of the methodology that we used in the previous lesson. So I'll pull up the model from the previous lesson to explain this a little better. Right, so if you recall from the previous lesson, what we did when we modeled this coupling is we went into model and we set the material, the shear modulus to 0 because we had the we had the stiffness information provided to us by the coupling manufacturer. So instead of allowing DIROBES to internally calculate the stiffness values, we physically put in the stiffness values over here under the torsional/axial tab. So we'll do the same thing in this particular model, but there is one key difference in this particular model. In this model, we have more than three elements model for this particular coupling, right? So in this case, we have in the previous model we had one, two, and three elements to represent the entire coupling. But in the current model that we're building, which is shown right here, we have more than three elements for the coupling. So how would you model a stiffness for each of these hubs and stations in between these hubs if you have more than three elements, and essentially if you have more than three springs, while the manufacturer has only provided you three springs? So there are a couple of ways of doing this. One way is to change the shaft element table right here of the coupling and uh, convert it in such a way that you have exactly three elements here by using more sub-elements, and then you can then come here and model in the three springs exactly like how we did in the previous example. Now, since I've shown you how to do this sort of methodology in the previous example, what I'd like to do is show you another way in case you have a situation where you have more than three elements to represent this coupling. So in our case, we have, I believe, about seven elements that are modeling this coupling. So 1, 2, 3, 4, 5, 6, 7. So there's seven elements that are representing this coupling. So what you can do is you can convert the equivalent inertia of this coupling, which is given to us right here, and we can convert it into seven equivalent springs. So really, we're not changing anything much here. The coupling manufacturer has his equivalent inertia number right here, or sorry, his equivalent stiffness information right here. And what he's done is he has just converted them into three springs, which give us the equivalent stiffness. So all we're going to do is, instead of using three springs, we're now going to convert this equivalent stiffness into seven springs. So I'll show you how to do that. So we know our equivalent stiffness of the coupling is 2.84 e to the 7, and we want to convert it into 7 equivalent springs. So all you do is you take 7 and you multiply it by the equivalent inertia, sorry, the equivalent stiffness, and that will be the stiffness of each spring in your coupling. So, and I'll prove this to you. So if I were to take this and if I were to copy this over 7 times, right? So each of these seven springs, if I were to add these seven springs up in series, they will give me exactly the stiffness of this particular coupling. So let me prove that to you. So we have seven springs. I'm going to do the 1 over k method again that I showed you earlier, and I take the inverse of these seven springs divided by that, right? And then I do the sum of the 1 over k, which is sum, and then I take the reciprocal of the sum, which is the inverse again. And there you go, you have 2.84 e to the 7, which matches exactly the stiffness information of the coupling given to us by the manufacturer. So all we've done is we've taken this stiffness information, and instead of using three springs like what the manufacturer gave us, we are just going to be using seven springs because we modeled the coupling using seven springs. So let me show you how you do that. So recall that when we modeled the coupling in, we had to go in and change the material information of the coupling because we're not going to let diarobes calculate the stiffness information for the coupling. We will set the shear modulus of the coupling to 0, right? And then we go over to the torsional / axial and we click on linear connectivity and we model in the spring stiffnesses for 7 coupling stiffnesses. So in this case, our coupling started from element number 25 and ended at 31. So we'll start with modeling those springs in. So torsional, it'll be station number 25 to 26. Flexibility, and stiffness will be 1.99 e to the 8. And so that'll be K1, and then torsional 26 through 27, flexible 1.99 e to the 8, K2, and repeat this for the next 7 elements of the coupling. And your final table should look like this. Right, so now we have 7 stiffnesses modeled for each of the elements in the coupling, and each of them have a value of 1.99 e to the 8, which, if they're summed in series, will give us exactly the equivalent stiffness of the coupling. So hit OK, hit save, hit close, say yes, and there you go. Now, if I were to zoom in, it's a little hard to see, but the springs that we put in are now connecting each of these elements that represent the coupling. And there you go. This is your final model um, of the motor that is coupled to a pump and is driving this pump. And I showed you a different method of inputting the stiffness information of the coupling in situations where you have more than 3 or 4 elements to represent the coupling. I showed you how to put in the information for the rotor core, and I also explained to you what's different about this particular element here, where the manufacturer provided us an equivalent geometry information to give us the inertia and stiffness information for this particular impeller. And so that's how you put together a full model of a particular drivetrain that you're interested in studying. Now I know that you have the demo version of Dyrobes, and so you will not be able to calculate the torsional natural frequencies of this particular model and see the interference diagram, but I will post the natural frequencies and mode shapes of this particular model for you to review and see what it calculates out to. So I hope you enjoyed this lesson. This is the last lesson of this course. I will be posting other modules and other lessons and other case studies on the website, and I hope you keep visiting this website to learn more about torsional information. But as far as the particulars of this course, as far and learning the fundamentals of torsional vibration, I've covered a lot of concepts here on torsional vibration analysis, and you should be able to put together a very simple model or a medium complexity model and calculate the torsional natural frequencies and look at the mode shapes and look at the interference diagrams and get a general idea of what the torsional characteristics of the machines are. If you have any questions regarding torsional analysis or any general questions regarding vibrations, please feel free to reach me at any time. I'm always happy to help you. And please look out for more information on this website. I will be adding an advanced torsional vibration analysis course this year for those people that are interested in learning torsional vibration analysis to its full extent, because what we've learned here are the fundamentals. But if you want to do a torsional analysis to the point of doing a forced response analysis, to do a steady state analysis, to do a transient analysis, to be able to predict stresses in your drivetrain, then I will be teaching a advanced torsional vibration analysis course this year, and I hope that you can join me for that particular course if you're interested in learning more details about torsional analysis. So thank you very, very much for joining this course and for giving me a chance to teach you torsional analysis. Please reach out to me anytime you have any questions regarding torsional analysis. Thank you very much. These modules will be available for you anytime to view and to review, and you're welcome to log in at any time. So if you have any other further questions for me, please reach out to me. Thank you very much. Take care. Bye bye.